In this video, we're going to look at creating orbit diagrams using GeoGebra. The objectives of this video are to review what orbit diagrams are and concepts related to orbit diagrams, provide a process on how to make orbit diagrams in GeoGebra for those with minimal experience with GeoGebra, and provide a process on how to make orbit diagrams in GeoGebra for those who are proficient with GeoGebra commands. Specifically for this video, we will be using GeoGebra Classic 5. Orbit diagrams. An orbit diagram for f of u of x will relate to the value of the parameter u with the fixed or periodic points associated with that value. The horizontal coordinate of the diagram is based on u, while the vertical coordinate of the diagram is based on the value of the fixed or periodic points at u. A solid line is used for attractive fixed or periodic points, and a dashed line is used for repelling fixed or periodic points. However, whenever we use tracers in GeoGebra, we don't have the ability to try and change these to dashed lines. Therefore, we change our code. In this case, for our diagrams, we'll be using blue for attractive fixed or periodic points. We'll be using red for repelling fixed or periodic points. Just to recap, a fixed point x0 is in a domain of f of x when x0 when f of x0 is equal to x. x0 is a periodic point at period n when the nth iteration at x0 is equal to x0 and any prior iterations at x0 are not equal to x0. If fn is differentiable at x0, then x0 is attractive when the derivative of the nth iteration at x0 is less than 1, specifically we're looking at the absolute value, and x0 is repelling when the derivative of the nth iteration at x0, the absolute value of that, is greater than 1, and we can't really say anything when we have that it is equal to 1. At this point, we're going to take a look at a process of how to make an orbit diagram for those with minimal experience in GeoGebra. First, define f of x based upon a slider u and define g of x is equal to x. Set the interval for u by adjusting the values of the slider. Set the slider increment and speed of u, recommended to be 0.0001 and 0.1 respectively. Adjust u and use observation to identify the point of intersection for each f of x equal to g of x, and that's for whatever iteration we're looking at. In the first one, we're looking at f of x equal to x. For each point of intersection, add the point u, and then we're taking the x-coordinate of the point of intersection that we're actually looking at. Step 6, we define dynamic colors for each point of intersection based on the absolute value of the derivative of the nth iteration at that point of intersection. For each point from step 6, we're going to enable the trace, and then we're going to hide the point so that we don't get confused. After that, we're going to define f of n, whatever it is, for n2 or n3, and we're going to repeat steps 4 to 7. Once we're done with putting on all points that we want onto the diagram, including the tracers, we start the animation. Just as a quick little note, we get to see here an example where f of x at x squared plus u between 0 and 0.5 shows the importance of setting the right speed and increment. This is an example of having a speed which is too fast. This is an increment which was slowed down significantly, but the increment was too large, and we get gaps in our graph. And here we've got a small increment and slow speed. We see that it's very smooth and it didn't miss anything. And here's what the actual orbit diagram looks like if we were to have it with dashed lines. We're now going to turn our attention to using this process to create an orbit diagram for f of u of x equal to u of x times 1 minus x, where u is equal to 0 to 3.5. To start, we have the input bar on the bottom. We'll be putting in f of x is equal to u times x times 1 minus x, and pressing enter, which then defines it. It will prompt to create a slider for u, in which case we want that to happen. And so what this slider does is allows us to adjust the value of u. Secondly, we need to define our function g of x is equal to x in the same process in the input bar and pressing enter. From here, we need to try and change the interval for our value of u by adjusting the values in the slider. We can do this by right-clicking on the slider and going to the object properties. We want to have this value of u between 0 and 3.5. remember, we set our increment to a very small amount, which is 0.0001, and our speed will be set to 0.1. This makes sure that when we animate, it's going to go slow enough that we won't miss anything or have gaps in our graph. The next step is that we have to try and find out the points of intersection. And what we want to do is we want to animate this and see where we're going to have points of intersection. So if we zoom in a little bit further, we're going to see 2 points of intersection, which is 0 and this second point over here. We've got this intersect command at the top, which will then identify where these two functions meet. So now that we've found our point of intersection, we now need to add some points to the graph, and these are the ones that we actually really care about. So we define our points as u and then the x value of a, and we use a capital for a because we're looking at the x value or x coordinate of a. Enter. We need to do the same thing for x of b. And so what you start to see is that these 2 points here have now come in. And as we slide and adjust these, the slider u, we can now see that these are being adjusted. But now we need to change the dynamic colors. So we go to the point that we want to change. C is based on A. So we go into the advanced settings, and this is where we need to use the ABS for absolute value f prime of x. And this is where we want to have the value of f prime of x, but we don't want x. What do we actually want to have? We want to have the x coordinate of a in here. And this is really important because what it's doing is it's calculating the slope of this function at a. And remember, we have red is for repelling points. So this is where it's greater than 1. Press enter and we're good with this. We're going to copy and paste this down to the other 2 lines. In the middle one, when we're dealing with booleans in GeoGebra, we actually need 2 equal signs. And then the last one is when we have blue for our track to fixed points, which is less than 1. Okay, so right now, as we try and move this, we start to see it is just red all the time, which means that is a repelling point. And we do the same thing here for our value d, except with d, this is now based upon b. So we copy and paste, we change this to equal, we change this one to less than, and maybe we'll see some functionality with this. And we notice that it did turn into blue. So last thing that we have to do is we're going to hide these points. We're going to show object, they're going to disappear, and there's a reason for that. And we're going to turn on the trace, and we hold down the control key to select both at the same time, trace on. And so what we start to see here is our fixed points for our orbit diagram. So our next step is we're going to hide f of x, and what we're going to do is we're going to define f2 of x, and we're going to repeat this process. So f2 of x is equal to f of x times f of x, and we start to see it come in here, and we're going to slide this around and see where our points of intersection are. Right now we do see that there are 1, 2, 3, 4, and so we're going to put those on, and again we're going to go back up to our intersect function, 1, 2, 3, 4, and we're going to then have to try and change our commands for these. Oh, that's not it. We're going to put in u at the x value of e. There's our first one. U at the x value of f. U at the x value of g. And u at the x value of h. And what you really do start to find is that even with such a simple function, that this is very tedious, even with just period 2 points. So the one thing you will find is, while this is tedious, this is actually can be quite a bit simpler than trying to do this algebraically. From here, what we're going to do is we need to find those points. Where did they go? Well, they're over here. So what we're going to do is we need to try and change the dynamic colors again. And we can also use here to try and do that. So we know that L corresponds to H, so we're going to come back up to here. And this is a big change. We need to make sure that we're doing F2 prime of X. And that now we're going to be looking at H And so now we can take this and copy it down, paste, 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 equals, and we're going to change this to less than. Okay, and so now we've got that point done. And I'm going to pause the video and I'm going to basically do the same thing for kj. And I'm going to come back after I've done that. So now returning, just to reiterate that L was based on H, which we see here. Our K value was based on G. Our J value was based on F. And our I value was based on E. We can go ahead and make sure that these tracers are set to on, which they are now. And at the same time, we can hide these points E, F, G, and H as they're no longer needed. So show object. And now what we can do is we can start to use our trace function. And so usually we can put this at the far left and click animate. And what we're going to start to see is that our function is slowly changing. And if you want to see visually what's happening, you can also show f of x and our f2 of x as they come in. And we also notice right now that k and l are undefined, and that's because as this comes around, these curves haven't yet touched up here, so we're really just stuck on, it looks like, only 2 points for our diagram. And then as we go along, this is going to keep on going. We do have the ability to speed this up if we wanted to. You can select the slider and you can change this to 0.2, and it really does depend on what the function is doing. For example, if I had set this to 0.3, it would actually probably have gaps in it because the slope is so much larger. But as we get into these very less steep or shallow slopes, that we actually have a very nice smooth curve coming in here. And it really comes up down to you on also how thick you want these lines to be. You can make them smaller if you want them. And that is how you make an orbit diagram with minimal experience with GeoGebra. We're now going to change our focus to looking how to make orbit diagrams with GeoGebra using more elaborate commands. This is the process that we're going to follow. So we're going to start by defining a function, and we're going to start with the function that we used in the last example, which is f of x is equal to u times x times 1 minus x. And this just allows us to try and put something in, and we can change this up afterwards. We're going to define variables in place of the actual parts of the slider, and this gives us more functionality if you want to include some buttons to try and change up what actually goes on. We're going to have minimum of u is equal to 0, minimum and maximum of u is equal to 3.5. We're going to have the speed of u is equal to 0.1. And what we can do is we can automatically take these characteristics, go into the object properties, and we can put them in here. Min u, max u, speed u. So if we want to try and change up what's happening with this slider, we just have to change these values here, and that can be really useful. Alright, and the next step, we have to introduce the variables, the y values for the window. And so we're looking to try and pull the y values for the window from here and here. So in this case, we got min y is equal to the y value of corner 1. And I'll explain this in a moment. The max value of the max y is equal to the y value of corner 3. The corners go as such: corner 1, corner 2, corner 3, corner 4. So when we pull these values, we're pulling the y value of the lowest y value down here and the highest y value up here. And we've defined them as min y and max y. And this will be useful when we start to look for points of intersection. Next, we need to open up our spreadsheet, and we're going to create a index. And so we're going to have 0, and then we're going to set up this A3 is going to be equal to A2 plus 1. And what this allows us to do is we can then take it and Control V to copy these values downwards. And this is going to be really useful for us when we want to try and index. So let's just expand this out. And up at the top, we've left row 1 open and available in case you want to identify or create labels. So like this would be period 1 points, which are technically fixed points, period 2, period 3, And you could put in numbers and even put that as a function if you really wanted to. What we need to do next is we need to try and fill these columns in. So how exactly are we going to do that? Well, we're going to be using the intersect command, and we're going to be creating a list. So we're going to create a list based on periodic point pt1 is equal to, and we use these brackets to create a list. We're going to use the intersect command, intersect, and we want to find the intersection of f of x with x. So that's where we're going to find out where it intersects the line, and we're going to use our minimum y value and our maximum y value. And this will create a list of points. And right now it comes up with this question mark because it hasn't got anything. But as we move this around, we start to see that in fact it does have these values coming in. So let's explain why we use min y and max y. When we think about what we actually see, when we actually input the values of u, and then the next value is going to be the y value, which is actually the x-coordinate. So the x-coordinate should be at lowest whatever we see here and the highest whatever we see here, because it's getting transposed when we put in our values. And that's exactly what we're going to be putting in here into this column B. So with column B, this is going to be a little bit more complicated, but I'll explain what's going on. So we're going to make a new point, and what exactly this is doing, let's take a look at the command. This is making a new point with an x-coordinate of u, and then we're pulling the x-coordinate from this list of whatever this list indexed at A3 is. So we see that this A3 is 1, so basically it's pulling the x-coordinate of the very first point. So if we were to look at this, then it's pulling, this here is our first point of intersection, so it should be 0 for the y-coordinate. If we were to fill this down, control paste, what we see here is it's the x-coordinate or y-coordinate. It really doesn't matter because we're joining on y equals x, and you see that it's the x-coordinate here. Before we start to fill these down, we do want to change some of the functionality of what's going on. In fact, we don't need to have these things shown, but we are going to want to have these points shown as they are being used to create our orbit diagram. So we're going to open up our object properties, and we're going to need to go into our advanced scripting to try and change up what exactly is happening here for our red, green, and blue colors. So remember that when we have repelling points, we're going to have them red. This is when our prime, our slope at that specific point, is going to be greater than 1 for the absolute value of it. And what this function is doing is it's saying take the slope of f at the y-coordinate of B3. And it's referencing B3, and it's referencing this 0 right here. And we're actually going to want to take this formula, copy it down, and just change the signs. So this will be equal to, and for the blue we're going to have less than, and so blue will end up being the attractive points, whereas the red will be greater than 1. And what we start to see here is we've also got the ability to trace, and now we've completed one point. And so if we were to take this and fill it all the way down, we can have 37, up to 37 points come in without doing very much work at all. In fact, so what we can do is we can end up hiding the labels, so that just makes it have a little bit of a cleaner look. In fact, if you wanted to change the size of these points, right now they're defaulted I think to 5. If you want to change them, you can. But what we can see now is that we've now got this cool functionality coming on that we can now do, but we've only captured fixed points. And so we can use a similar process to create column B. So we're going to need to define f2 of x is equal to f of x. Okay, so now that that function's there, we can use the similar process. So we've got period point 2 is equal to, and this is where we want to use our list. So I've just copied the code from the first period point 1, and so instead we're going to have, instead of f, we're going to have f2, and so this is going to create a list of points of intersection where f2 intersects x. Our next step is to try and go over to column C, where we're going to then use a similar command of what we used here. So if we were to take a look at this formula, we only need to do a slight adaptation in this column to make it work. So instead of using a period point to period 1, we're using period points of period 2, and we're now pulling from this new list. And now we need to also change the advanced color settings. And this becomes very similar to what we were doing before. So we're using the absolute value of, in this case though, we're using f2 prime at that y value of c3. So we're taking the y value here, we're pulling it out, and then it's going to turn it red if the absolute value is greater than 1. And we can copy and paste this down, we can change the signs, and then essentially we are done with period 2 points. And less than 1. Okay, cancel. Okay, that should be good. What else do we want to do? We want to make sure that the trace is on. We can take away the label to give it a nice cleaner look. We can take this, copy, and paste it down. And now we have up to, right now, 39 points coming in that are period 2. Let's just take a look at the graph, see how that's coming along, if there's anything new coming in. Well, we do see some new functionality coming in here, which is pretty cool. And if we want to, we can do the same process for period 3 points. What works really well for this method is that if you want to change up f of u to something else like x exponent u, you can do that. And unlike the previous method where we're doing everything visually, the computer is automatically calculating these points of intersection. So what we can do is then we can see that we actually have these points coming in. We also have the ability to change our minimum u and our maximum u, so we're going to go to -2, and we're going to go to 2. And swing this around, and we also have the ability to animate. Animation is on, and we can see that it's slow. And what you can do is you can also change the value of the to be changed upon buttons. So like things like animate buttons and speed up, slow down. You can do a lot of cool things, and you can have inputs for these so that you don't have to actually double click and you can change it on the fly. So we're going to pause this, and I actually want to speed it up. We're going to go to 0.25, enter, play, continue animate. And so the one cool thing about what you do see here is you do see this vertical line come in. We do see our fixed points. And that's pretty much it. I mean, if you want to continue on this process, you can go to period 3, you can go to period 4. I would caution that going to period 5 and beyond could have a very high chance of crashing the computer. Now that we've just created our own working orbit diagram in GeoGebra, I want to go over the limitations. Overall, we have a final product. This is what we were able to create in a few short minutes that we had with you. This is what we end up having in the end. So what are the main differences? Well, we also notice down here with this function, x of u, that we are missing these points down here. And that's because GeoGebra does seem to have some sort of bug when we have that function equal to 0. So we manually input it and check for when it's equal to 0. The other thing which we added were some functional buttons. So when we click on this button, it will start u off at the beginning. We can decrease the speed of the animation or increase the speed of the animation. Even if we continually click on this, we'll actually start to go backwards. We have an ability to pause, and we've created inputs for our boxes. It just makes the user interface that much more functional to see what exactly is going on. So we conclude with what we were able to achieve. Some of our goals in this course were to see if we could recreate some of the orbit diagrams we encountered throughout the course. So on the left is what we found and know to be true based upon the course notes, and this is what we were able to create using our orbit diagrams. Again, x squared plus u, and what we were able to create. This here is ux plus 1, and we do notice that with this orbit diagram we are missing vertical lines. It is a limitation of this program. And xu, we sometimes saw the vertical lines and sometimes didn't. And some other cool ones which we didn't have orbit diagrams to confirm, but they're just cool, so we decided to throw them in. Some of the limitations include the following. The orbit diagrams by observation were tedious to set the colors for each point of intersection. It could involve human error if you copied and pasted something wrong or referenced the wrong cell. There were bugs in GeoGebra. Sometimes when you end up using the slider, some of the points of intersection would be redefined to other points and they would never come back to their original. Changing f of u of x usually results in POIs disappearing, and so this was a really big difference between the first model and the second model, is that when we end up changing up to a more advanced version, is that we didn't have to go through all that work again to try and find the point of intersection because they were already there. The orbit diagram using commands, well, here are the limitations for it. It draws red and blue instead of solid versus dashed, which is technically what we should have. The vertical lines didn't always come in, sometimes were visible. The computational power was based upon the limit of the number of periodic points, and as you started to go beyond 4, maybe even 5, some computers could handle it, but other computers couldn't, and that comes down to the computational power of the CPU. And there can be gaps. And that's it. Thank you for watching.